I want just to welcome everyone for this session, and I want to introduce my excellent friend Ruud van der Baas from Oracle Labs, he will say from where. It has been really a pleasure to have his friendship and support through all these years of Multicore World. This is the first year that he is not sharing with us open wounds, but we will. And someone is laughing around, so maybe you saw that. I will put it online one day. So please check Ruud's bio while you finish your muffin. You can go for another one. And please join me welcoming Ruud to the presentation.
Thank you, Nicholas. Thank you. Thank you. It doesn't happen often I get applause for having done anything, but thank you. First of all, there's a reason that this picture is there. That's to publicly embarrass Nicholas. As much as I like Christchurch, this will be for Multicore 2025, Nicholas. That's where I will be. So you can work on it. You got a year. Yeah. All right. Let me get started. I have quite some material, but I'll try not to rush things and still stay on time. So I had 50 minutes, wasn't it? Yeah, thanks. Okay. As Nicholas incorrectly said, I'm not part of Oracle Labs, which is a pity because then I could have claimed some ownership of the coffee. I'm actually part of the Linux engineering organization. And in my day job, you can read it, but in my day job, I work on a profiling tool. I sneaked in a little bit of a promo here and there. It's an open source tool, so I always say I get 10% of a free license. So it's a GNU tool, and but you will see some usage of that tool in my talk. I'm going to talk about performance tuning, which I've done a fairly large part of my life. It's a bit of a frustration talk, but I'll try not to share my frustration too much with you. So this is the sort of general outline. I quickly adapted the timings to be accurate. So first of all, of course, some motivation. Then I felt compelled to talk about AI. I didn't feel compelled to talk about AI in a positive way, so we will see. Then we'll go into the more technical details, and then at the end, we usually call it summary, but I'll just repeat myself literally. And then we'll have, hopefully, some time for Q. I always find it funny to see Q&A as if I pretend to have an answer to all questions thrown at me. I'll do my best to answer your questions, but I don't pretend to always have one, certainly not one that makes sense. So for those of you that really can't wait to get back on email or do your online shopping, I thought I'll start with the summary. So this is be shown at the end again. I want to have a plea for people spending more time on tuning their applications. Why? First of all, it will save you money, as I will show on the next few slides. It will, of course, reduce your development time for whatever you're doing and or the quality of your product. You can do more accurate simulations, for example, if your application is faster and you don't need to wait 6 weeks for the result. Another thing that I haven't heard anybody talk about, but when you talk with somebody who does the performance analysis, that person can exactly tell you what you will need in your next system. That person will know, like, yes, we could benefit from larger caches. No, it doesn't matter because we're streaming through the data and the size of the cache almost doesn't matter. So you will have a better understanding of your future needs. And that's very valuable information because it dictates sort of where you go instead of blindly buying whatever is offered to you. The other thing that I think is most important is you can educate your developers to start writing efficient code from day one. So whenever they type in, they have some notion of performance. It doesn't have to be perfect, but it's certainly better as what they're usually typing. So this is the summary. Get your application performance expert today. So the motivation. Why talk about performance? Well, here are some things that have been thrown at me at the past. We got such smart software. We have compilers. They will fix my inefficient code. Well, as it turns out, compilers have a very limited visibility of your code. They can do magic on this kind of code scale, but when it starts the bigger picture, they literally don't see. So compilers, yes, they have gotten more powerful, but they're still inherently limited in what they can do. On the other side, well, compilers have no clue, so I need to write everything myself. I still have that tuning book written in the 60s. It's extremely valuable, and I write unreadable code, but it's really fast. Well, even the latter is not true anymore because, again, go back to that compiler. If the compiler can figure out your intentions, it can make a better decision. There's no doubt about that than you can. And it will do so across the platforms that you're using. So that's another thing that's definitely a myth, fairly persistent. This is probably the most popular one. We'll just buy a faster processor. Well, I'll talk about that in a minute. It's called Amdahl's Law, why you shouldn't wait for that. This has been literally told of me. I'd given a performance tuning class at a very prestigious institute in the US. So prestigious I wasn't even allowed on site as being that bloody foreigner. But I didn't mind. We were in a golf resort, so I didn't mind that decision. And one of the groups didn't show up. So our people went there, and they talked to the manager. They said, well, you're doing that. You're going to do that really large software development project. Why was nobody from your team there? And the manager literally said, oh, we'll do the tuning when we're done with the code. Well, that's about as bad as you can get it. And then, of course, AI. AI with all its magic, and I have been involved. It wasn't called AI then, I'm too old for that. But we try to have smart systems to do that. And I'll say a bit about that. Why so far I've only seen those fail. So we'll get to that. Now here's the thing that is probably the most common one. It's just too expensive. I can't afford to hire somebody or reassign one of my people to be my local performance expert. Now, let's do some very, very basic math. And I went online, and this happens to be Amazon, but that doesn't matter. I needed some pricing on cloud. So take this with a bit of a grain of salt, but certainly the order of magnitude should be right. So I went and I found a compute-optimized instance of the 7th generation. That's the AWS Graviton ARM-based processor. I'm using one in the US, in North California, because the pricing is dependent on where your data center is. Because initially when I tried to reproduce my numbers, double-check them, I couldn't find them because I was looking at the Kentucky pricing. It's cheaper to do your computations in Kentucky than in California, which is kind of interesting. Probably Adrian will know a lot more about that. 16 virtual CPUs. I won't go into the notion of virtual CPUs, but it's like 16 cores maybe, or 8 with 2 threads. 32 gigabyte of memory, so fairly small. And here's the cost per hour, and that translates to about $6,000 on a yearly basis for that instance. Now let's say you're going to hire a performance geek, and you're going to pay that person $150K a year. What I'm showing you here is your profit. Your profit, so literally vertically the amount of money saved as a number of the number of virtual CPUs that you're using. You're supposedly using a fairly large cluster. I went all the way to 2048. And what I'm showing you is your saving. You're saving as a function of how much you improve the performance. So the light blue line says if you manage to make your code go 20% faster, you still have to pay that person, whether he or she was successful or not. So the break-even point is fairly close to 2048. If you make it 25% faster, as soon as you have 1,500 cores or more, you start saving, and eventually you'll save $50K saving on top of that salary. And likewise, if you can do 30%. Now, why did I pick those numbers? In all of what I've seen tuning other people's code, that's a very conservative number. There's a lot of low-hanging fruit out there, and admittedly, low-hanging depends on how tall you are. But low-hanging fruit, a lot of opportunities to recompile, change your compiler, do some tuning, some environment variables. 20 to 30% isn't all that much. Usually the savings are greater. All right, having that out of the way, as I said, I want to talk about AI. And yes, I have my own interpretation of AI. It's always incorrect. The question is how close you are. That's, I think, a better question to ask. So let's talk about AI. Why am I so skeptical in this field about using AI? First of all, you don't know what the reference is. So what I'm now showing you is like my doubts when I start looking at an application to tune it. You have, for example, all these processors have counters, and they tell you exactly, more or less, how many cache misses you have at all the levels. My counter question is, so what? I can have a tool that will tell you got 1 billion cache misses. Great. Is that good or bad? Tell me. It's really, really hard to find out. So you miss a reference, and there's ways around it to try to find it. So the question is what you observe normal? And to illustrate that for a high-level audience, I'm showing you 2 pictures. This is seismographic data, and definitely you don't want to see outliers here. That's not good news, as you all know. I know I'm in New Zealand, so you see this on an hourly basis. This is bad news. But here, you probably want to see an outlier once in a while when they're measuring your heart. So it all depends on the reference. And again, you don't know where you are. So keep that in mind. Thinking about an AI system, what do I consider to be expected and what's an outlier? Very, very hard question to answer. Then let's look at architectures. And I made it fairly long, but this is a simplified architecture. I didn't even include GPUs in the mix that I'll be showing because they add a whole world of complexity to what I'm going to show you now. So we start, and I realized, am I the only one mentioning the word core in the Multi-Core Worlds conference? No? We're going to, okay. So here's the core that's doing all the computational work. The core gets its data out of data and instruction caches, and those have reasons to exist. They're fast, small memory buffers. And as technology progresses, there are multiple levels of cache, like there's a level 2 cache that shares data and instruction. And at some level, you have what's called the last level cache, which is closest to your memory. And that's why it's called last level. There's an explanation for why that is. And then you have multiple cores, multi-core world. You have multiple cores. And that's sort of the memory side, the computational memory side of your system. This is a fully fledged system. That's what like you got in your laptop. And the rule of thumb is regarding the capacity of the memory. Capacity increases as you move from left to right, but the speed decreases. So it's good for performance to stay close to that core, to keep data in those caches. So keep that picture in mind. We have the computational part here, and that's where you want to stay. Now, one of the things hardware architectures have done, they've given us hardware threads. It's a lot to say about hardware threads as well, but essentially it's a hardware acceleration. So each core has multiple hardware threads. That's part of the design. Some don't, some have it, some don't. So that's how it works. It sort of sticks to the core, and here's why. Here's a typical execution of an application. So the light blue application is running, and at some point there's a gap in the execution. It's not doing anything. The reason is it could be waiting for I/O or cache misses or whatever. Let's keep I/O in mind. So you have these gaps in execution. Then your time slice is up. The next application will come in and probably has a similar kind of pattern of execution and waiting. The whole idea, which is actually a really good idea behind hardware threads or hardware threads, is you get to use that gap to fill the time instead of burning energy and doing nothing. That's a very simple but really powerful idea. It works if your application has those gaps. It's a reason why some people are disappointed. If you have an application that doesn't have those gaps, adding more threads at it at that level doesn't help. But it saves you time. So you have these hardware threads as an acceleration to your core. Now, let's stick that design with those cores and those caches and those hardware threads into a larger system. So I got one what's called a node, and now I got 4 nodes, and I connect them in what's called a cache-coherent way. Cache coherency means that I can see everything that's going on. That's a proprietary interconnect that's really nice to have as a developer because you see like one big system. In other words, you see a single system image while the hardware is distributed. And that's why these architects are very popular. The reason to do it is that you have scalable memory bandwidth. Many HPC applications run out of bandwidth sooner than later. So now you add a node, you add bandwidth. And that's called a non-uniform memory architecture because the memory is scattered over the system. All those blue boxes is memory. To you, it appears as one memory. When you look at it with the tool, it will tell you this is your memory. It won't tell you that it's sort of scattered over the system. But one thing is there's a performance penalty depending on which part of the memory you get your data from. So that's one element. Now we take those boxes and we put them into a network, and then we talk about a hybrid multi-level parallel system. The way you program that is different. You can program the nodes with shared memory models like POSIX threads or Java threads or OpenMP or whatever. Over those nodes, you need to use something else, and the most common way to do that is MPI. So you have two levels of parallel programming in your system. And again, many users have these kind of systems. Well, you could argue, well, I'm not that rich. I do all my work on my laptop. Well, I couldn't get it ready for this trip, but I just bought a new Apple M2, or they got an M3 after that, but I have an M2, and look at what it has. In that one laptop, you have, they call it efficiency cores, 8 performance cores, 8 GPU, 19 core, depending a bit on the model, a neural engine, a media engine, and an image signal processor. That's how complex that laptop is. So what are you going to do when you write your application? How are you going to take advantage of that? You want to throw away? Actually, it happened. I was doing video processing on my new glamorous laptop. I enabled hardware rendering, and actually it was slower. So I paid Apple big bucks for that, and the software developer didn't care about using the hardware that I have in it. That's sort of the way things are. So you're not off the hook even if you have a smaller system. That's what I'm trying to say here. And now my question. AI. I throw my application at you on my 1 million lines of C++ code. Now, can you make it faster? I don't think in the foreseeable future we'll see any significant thing of that. The hardware is just way too complex to for that. But that's why we'll have the panel tomorrow, and after the break you can throw all your non-eaten muffins at me to discuss that. So, but if I go to somebody and I say, yes, AI can be trained, it can solve everything, so it can certainly solve this one. So my answer will be sure, let me know when it's ready. So let's go a little deeper. So this was sort of the driving thing behind this talk is we have all these very large parallel systems. They're out there. People buy them, larger or smaller. All of them are extremely powerful. These laptops are really powerful. Why don't we get unlimited performance? And again, we are in Nicholas's multi-core world universe, so I have to talk about that. Actually have to talk about a single core in your world, because why is that? And just a show of hands, who knows what Amdahl's law is? Okay, just a few. It's not a European Union law about the volume of vacuum cleaners. They actually have that law, I'm not kidding you. There's a European law that controls the volume your vacuum cleaner can make. Amdahl's law is something more from computer science. Let me show you an example. You have an application and it takes 100 seconds to run. And you've done your job, you've parallelized your application one way or the other, and 80% of that runtime can execute in parallel. That's not nothing, that's not small. That means that out of the 100 seconds, 80 seconds can be reduced, and if I use 4 threads, ideally that'll reduce to 20 seconds. That still leaves me 20 seconds, the part that I didn't touch. So my total runtime is 40 seconds, which gives me a nice 2.5x performance improvement, but not the 4x that many expect. And essentially that's called Amdahl's law. Amdahl's law says the part you didn't optimize, whatever it was, will get you sooner than later. And actually he didn't even quote it in terms of parallel computing. It was about, he wanted to get rid of vector machines because he didn't design one. That's why he brought it up. You can do science on it. This is pseudoscience, spreadsheet science, but let me just give you a feel for what I'm showing you here is, let's say I have a machine with 16 threads, and I'm going to show you the improvement, the speed up, as a function of the number of threads, as a function of how much work I did to parallelize my code. And the sanity check is the red line, that's 0%. I didn't parallelize anything, so I'll never see a speed up, of course, because I didn't parallelize anything. The green line is the 100%. I parallelized everything in my code. All the time spent had been parallelized. So you get the perfect linear speed up. The other lines are showing you what happens in between. And let me walk around because I've been standing too long, my watch is complaining. 95%. You've parallelized 95% of the runtime of your code, which is a lot. And what this says is you're stuck. The good news is always look at the bright side of life. It's not that hard to get some improvement in the beginning. That's encouraging, and that's exactly what you see. People start parallelizing the code. Hey, I got to speed up 1.5 and 2 cores. That's great. But so that is a good thing. But this is Amdahl's law, and it says in the 95% case, you will never get more than 10x. If you show that to your management, you'll never get that performance expert. So I would not show this to my management, but that's the reason why the part that I didn't optimize does matter, and that's executed on a single thread. And nobody talks about that anymore. Little frustration. Okay. Let me show you an example. And before I forget to say that, in this example is a lot of knowledge hidden. And this is not to show off at all. It's just to show you my skepticism towards AI handling this. Yeah, you need to come a long way. Well, we'll see. I'll be back next year, so we'll see. Maybe there will be another talk. It's from graph analysis. Graph analysis is sort of everywhere, used in all sorts of things, from counter terrorism to online shopping. Graphs are everywhere. And some years ago, I took the OpenMP reference Graph 500 benchmark. So it's no longer available, but I got it online. Here's what it does. First of all, it's an artificial benchmark, so it generates some graph depending on the parameters that you give it. Then it selects a key to search for, so it randomly selects a number. And with this kind of algorithm, it's a breadth-first search. It'll generate a tree as a result, and it will verify that that result is indeed a tree, so that the result is correct. And it does that by default for 64 randomly selected keys. That's what the benchmark is. Interestingly, that benchmark only measures the search time. Actually, the verification time is more expensive, but they don't care. They only look at the search time. So what I'm going to show you in my charts is the search time, not the verification. So here's an example of how that code executes. And this was made without tool, sorry. So what you see, time is from left to right. And what we do, we show for different functions, we show different colors. You see the dynamic execution of your program unfolding in front of you. So, for example, you see the graph generation. You see this little spiky thing. That's a recursive quicksort thing, but it doesn't matter because it's a generation of the graph. It's not part of the benchmark, so nobody cares to make that go any better. Then you go into the second part where you do the search and the verification. Next key, search, verification. So that pattern is repeated 64 times. And the green line is the operating system view. For those of you that wonder, green is good news. Any other color than green is like a page fault or something bad. So green is good news. So the operating system is happy with this application, and this is how it executes on a single thread. So I ran it on a very, very tiny, almost kindergarten instance, just 8 Skylake cores. The Skylake core, two threads, so I have 16 threads to play with. So very, very small. We're not talking about a mature HPC system here, a very, very small system. And what I'm showing you is the search time. That's the blue. The bar chart is the real time. That's the real money. That's how long we need to wait to get the result of your search. And the good news is it gets lower and lower. So the search actually benefits from even all the way to those 16 threads. So that's really good. But the parallel speed up, that's the black dotted line, is really low. The maximum speed up that I get is only 3.2 versus what I could get, and that's that other dotted line. So this is not really good. I used that tool to find time-consuming parts. If I had more time, I would share with you kind of things that I did, but it doesn't matter. I found several ways to... Actually, that program was so bad that it's a goldmine for OpenMP teachers. And I complained so bitterly that I think they pulled it out. It's no longer available on the line. But it's a goldmine for tuning opportunities. So, after fairly simple changes, this is what I got. The green is the new search time. Just look at the green time. And one of the interesting things is initially for one thread and two, you don't see an improvement. That's kind of, well, what a bummer. But then it starts to take off. So it gets better and better. So I go to 16 threads, and as you can see, literally my search time halves. So initially not much of a gain, but ultimately I'm 2 times faster. Here's the key question. Again, think about my AI comment. Are you done? Is this good enough? What's your limit? How fast could this be? Well, what we do in practice, we do multiple different experiments, try to sort of corner it, try to kind of isolate it, find out what's going on. And that's what I did. And here's what I saw. I'm comparing here the execution of 1 and 2 threads. I'm looking at the initial, the generation phase, faster, good, check mark. The search verification phase, faster, check mark. So both benefit from using 2 threads. But I started zooming in. And then what I saw was that let's focus on the two-thread run. So this is the main thread that's always running, and this is like the secondary run. In the very old days, this was called slave threads, but we don't call them slave threads anymore. We call them other thread, whatever. So we have the main thread, and then what you see here is these gaps. Gap is bad news. So the second thread isn't using the hardware in the optimal way. Oops, sorry. And when you zoom in, you see those gaps. Well, you also see, if your eyes are better than mine, it's always in the red part. It's always in the search part. So the search part has something for that thread to stop working. And I've done this as a professional for a long time. Sometimes problems just go away if you change the conditions. So maybe 4 threads is better. No, actually it's worse. Bummer. And if you zoom in more, you will see that always these gaps, and they're always in the search part. Well, at least that puts us on the trail of what to change. And so the search part definitely has a problem. And those gaps are summarized in this chart where I show you the distribution of the thread time. And let me explain that a little bit. So I got 2 threads. The first threads take nearly 800 CPU seconds to run. The second one only 581. Well, in the good world, they should be about equal because you really want to distribute the work in the right way. So what you see, it's getting worse and worse as I add threads. Yep. And that's shown in this ratio of the best and the worst execution time. As you see, it actually gets worse. So when I have 8 threads, the ratio between the fastest and the slowest one is nearly 2. So it's getting worse. So this is definitely not a scalable application. I'm not going to go through any of the gore details here. This is a actually somewhat simplified version of where all that time was spent. And what I want to show you is there's that outer loop, and it has a Pragma OMP4 at the top line. So this is an OpenMP parallel loop, parallelized using one OpenMP Pragma. And inside, you got all sorts of bad stuff. And again, I don't have time to go through all of that. But what this does is different threads do a different amount of work. That's called a workload imbalance. So not all threads do the same amount of work. The problem is that loop here, this one, tells the system to carve out equal slots to everybody. But not everybody needs that. And that's why you get those gaps. They're waiting. They got nothing to do. The other one got a lot more work to do and is waiting. Well, the solution is really simple. So let me just go through the last one. In OpenMP, you can change that. You change that one line that I was showing, and you say it should be more dynamic. That's essentially what it is, because this is not a regular workload. So one line change, and actually if you do that, you would go a different way. And here's what I came up with. This is the change that I made. I changed that in the code. So the OMP4 was augmented with this purple kind of thing, and I set that environment variable. And and I gave it this choice dynamic comment 25. Why do I have the magic number 25? Well, that's scientific ways crystal ball. You do trial and error. You try 50, you try 100. Again, my AI little devil in me says, how would you handle that in AI? Maybe some of you can discuss that. I would be interested in that. How do you detect that? Here's the final result. And a lot of stuff here, so I want to show you the history. Actually, on a single thread, it's a little slower. Would AI be happy with that? To make a change that actually makes the code go slower? It's only 10%. The reason is that dynamic handling of the workload is more expensive. That's why it's not the default. So it's a little slower, but look at what happens after that. First of all, I get near linear scaling, which I didn't get. I get a benefit from my additional threads per core. And the bottom line literally is that now my scalability is no longer 3.2, but 9.5, and the whole code is 3 times faster. And again, in the panel or after this, I'd love to have discussions about people that are more knowledgeable on AI than I am to see what you could do here. Because it is interesting. It would be really nice if somebody can crack it. Oh, yeah. This is confirmed in this chart. Now you see they all do the same amount of work. So we're done, maybe, because I don't know. Okay, for now I'm done. So I'm just going to repeat myself. I hope that I show you at least that you can save money, unless you pay that for an outrageous amount of salary to that person. You can actually save money, but it also improve your position in whatever you're doing, and it'll position you better for your future, and hopefully that person can train your developers to not write that really dumb code, because dumb code usually gives dumb performance. So get your performance expert today. Oh, yeah, sorry. We still had a discussion about AI, wasn't it? Any progress there? No, you're still working on it. Great. Okay, let me know when it's ready. Maybe Multicore 2025, when I hope Nicholas will invite me back. Thank you very much. It was very quick. It was more like to steer the thoughts than anything else. I'd love to talk about details. I'll be around longer than you like, and always happy to discuss. Thank you.